Hello everyone, welcome to another physical science lesson. We're going to be revising electrochemistry today. So let's go and have a look at what we're doing. So in our electrochemistry section, we recognize that there are a whole number of things that we need to know. And the most important thing is to recognize that there are two types of cells. There's the galvanic cell and the electrolytic cell. And these are all driven by redox reactions. And that's where we're going to start. We're going to recognize that in both these cells, there are redox reactions. So let's go and revise a little bit about redox reactions. Do you remember what they are? I'm sure you do. But here's something just to prick your reminder and recognize that within electrolytic cells or galvanic cells, we need an electrolyte. And the electrolyte is just a solution that conducts electricity. So in other words, there's a movement of charge that can take place within that solution. So typically, a salt solution, something like copper chloride, or even something that is molten, like sodium chloride that's been melted. We've got ions that can move. Electrolytes are generally aqueous solutions. They're generally dissolved in water because water is a polar liquid and it can pull those ions apart, and those ions can then move through the solution. And it's within these solutions that we get redox reactions taking place. If we were to summarize redox reactions, they are a type of chemical change that takes place, and within the redox reaction there are two half reactions, an oxidation half reaction and a reduction half reaction. We recognize these are taking place because there's a change in oxidation number. And that's really important. You should be able to identify, based on the rules of assigning oxidation numbers, where there is a change. But if you've forgotten those rules, it's not too much of a train smash, because you should also understand that there is a set of redox reactions or half reactions that is found on the standard reduction potential table. And these help us to identify what reactions are taking place. They're usually between the ion and the element. And so we can identify these, and not only identify where oxidation and reduction is happening, but also understand that there's another term. In describing these, there are always oxidizing agents and reducing agents. One of the things that is present at the start of the reaction is an oxidizing agent, and the other is a reducing agent. The agents make the thing happen that they're talking about to another species. So if I've got a reducing agent, it will reduce something else. If I have an oxidizing agent, it will oxidize another thing. And in that process, there is this exchange of electrons. And so by definition, we're saying that a redox reaction all involve a transfer of electrons. There's a change in oxidation number. Now, if you think about it very carefully, you'll recognize that there's either an increase in oxidation number or a decrease in oxidation number. Let's have a look at an example. So if we take something like zinc, that is going to form zinc ions plus 2 electrons, you'll recognize that the oxidation number of any element is 0, and the ion has the same oxidation number as the charge on it. So in this case, you recognize that what has happened is there's been an increase in oxidation number. And when there's an increase in oxidation number, can you see what's happening? There is a loss of electrons. And that means that the electrons have been lost. This is an example of oxidation. Now, the other is true. If we were to take the opposite reaction, a reaction in which there is a gain of electrons, in other words, reduction is taking place, we'll notice that the oxidation number decreases. And that is reduction. And so be very clear about the identification of oxidation and reduction. The important thing is to remember that oxidation always involves a loss of electrons. And that is the important stuff here. That in any redox reaction, we can have two half reactions. Oxidation is the one in which there's a loss of electrons. And we remember that by remembering OIL. Remember, this is a mnemonic. This is a memory tool. And sometimes you can get confused in a test or exam. So remember OIL. It tells you oxidation is a loss of electrons. And in the same way, we can say reduction is a gain. So we remember oil rig as being the memory tool to help us remember oxidation is a loss, reduction is a gain. Now that we've got that clear, remember that we are also given the table of standard reduction potentials. These are all written as reduction reactions if we read them from left to right. Let's go and have a look at the table. And you will see on the table here, they are written, as I said, reading from left to right. Let's take that one as an example, the magnesium one. You'll see magnesium plus 2 electrons gives you magnesium. Notice that there is a double arrow here. That double arrow is telling you that both reactions are possible. Magnesium ions can gain 2 electrons to make magnesium metal. Now, because it's gaining electrons, we would recognize that as reduction. But if we read it in the opposite direction, in other words, if we started with magnesium and we went in that direction, then we're saying magnesium loses 2 electrons. They're the electrons that it's lost, and it's making magnesium ions. That is the oxidation reaction. So when we write that, we can say magnesium goes to magnesium 2 plus 2 electrons. Now, in that case, recognize that magnesium is undergoing oxidation. So it's important to be able to move from the table of half reactions where there are these double arrows, and you can read from left to right, which is showing the reduction reaction, or from right to left, which is showing the oxidation reaction. What makes this even more interesting is to recognize on the table that there is an ability to oxidize or an ability to reduce that is shown on the table. So if you look at the table, you'll see that over here it says increasing reducing ability. That tells you that these things on the right-hand side, they are good reducing agents. In fact, they're the strongest reducing agents. Whereas if we go to the left-hand side at the bottom of the table, where fluorine is, this is where you have your oxidizing agents. And notice what the oxidizing agents do. They take electrons. And so if we go back to our definition of oxidizing agent and reducing agent, very clearly we recognize that the oxidizing agent takes electrons. We say OAT, oxidizing agent takes electrons. And I always look for the example of fluorine. So fluorine, it's on the bottom on the left on that particular table. It's the strongest oxidizing agent. It loves electrons. It wants to take electrons from anything. Now notice what happens when fluorine takes electrons. Fluorine will take 2 electrons and it will form 2 fluoride ions. Now, as it's taking electrons, what is happening to itself? Well, it is making something else. It's taking the electrons away from something else. So it's oxidizing something else. But notice what happens to it. It takes electrons and it undergoes reduction. It is reduced. Because it's taken the electrons. It doesn't just take them and leave them on the side plate. No, it takes them and it has changed. So anything that is an oxidizing agent oxidizes something else, takes electrons, and because it's taken the electrons, it undergoes reduction. So it takes the same way. A reducing agent donates electrons. Remember, we remember that by the mnemonic RAD. It donates electrons. And as it donates electrons, it is going to, as we've seen over here, undergo oxidation. It gives its electrons away, and so here you can see it's given them away. What's happened to it? It has undergone oxidation. So the reducing agent always undergoes oxidation itself. The oxidizing agent always undergoes reduction. Now, guys, the only way that you can get that firmly into your mind is to remember those mnemonics. Remember that you look for a transfer of electrons, identify where there's oxidation, where there's reduction, and you can then be able to pick up what species is donating electrons, what is taking electrons. And in that way, you can really get on top of these redox reactions. Well, you know what? I think that we've managed to sum that up quite nicely. Let's go for a short break before we go and investigate the difference between galvanic cells and electrolytic cells. We'll be back after this break. Welcome back, everyone. We're into revising electrochemistry. So far, we've dealt with redox reactions, which are a key component of electrochemistry. We recognize we can identify redox reactions, but now let's see that application to the different types of cells. We're going to do a little comparison between galvanic cells and electrolytic cells, and hopefully keep some things in mind. So, as we go to a galvanic cell, we have to recognize one of the key components of any electrochemical cell is energy transfer. So with a galvanic cell, you need to recognize that you start with chemical potential energy and you are producing electrical potential energy. So the chemical elements react to give us electricity. So a galvanic cell is just a battery. It is a chemical reaction that produces some sort of voltage for us that we can use in an external circuit. Initially, the current isn't very big, but we can put cells, multiple cells in series to get a bigger and bigger current. That's not our problem. What does this galvanic cell look like? Well, you can see it here. It's quite clear that there is no battery. There is a voltmeter that is measuring the difference in potential between the zinc electrode and the copper electrode. The part that is outside of the cell, outside of the configuration where the reactions is happening is known as the external circuit, where the parts of the cell where there are chemical reactions happening is the internal circuit. And notice in this case, we've got a metal electrode. In this case, it happens to be the copper with a solution over here that's separated by a salt bridge. That's all part of the internal circuit. Another solution and another electrode, which in this case was the zinc electrode. So you can see quite clearly there are two components to this galvanic cell. In this case, it's the zinc copper cell. Now, please don't get into your mind that we can only have questions on a zinc copper cell. That's not true. You can use any number of electrodes, a metal electrode into a solution of its ions, another metal electrode into a solution of its ions, and that electrode could even be a gas electrode, where there's gas passed over a platinum inert electrode, but there's a reaction that takes place between the gas and the solution. So it's very important to identify that. In this case, there is no battery, there's no power source, but we are giving external electricity out to the external circuit. If we look at the electrolytic cell, now what happens in an electrolytic cell is that we need electrical potential energy. We need a source of energy, and that energy creates a chemical reaction. So it's exactly the converse. It's the opposite transfer of electrons. Now, if we look at different electrolytic cells, you'll see they all look a little bit different. They also look different to the galvanic cell. Let's go and have a look at some diagrams of these cells. Here's one which was used to do some electrolysis. We started with copper 2 chloride, so we had copper ions in the solution, and we had chloride ions in the solution. And what happens is the chloride ions got converted into chlorine gas, and the copper ions got deposited over there as copper. Now, you'll see there's one container, and here's the key difference. There's a battery. This is the source of electricity. It's the thing that's making the chemical reactions take place. If you notice, at this electrode, this is a positive electrode, this is a negative electrode, and we've got some chemical reactions happening. There's no salt bridge. There's no two components. There's one component, one solution, electrodes. The electrodes over here, in this case of electrolysis, can be anything, but they are usually graphite electrodes. Okay, if we look at another example, we will recognize that in these different types of cells, the cells have names. They have the name of an anode and a cathode and a salt bridge for a galvanic cell. So if we look at the galvanic cell, we have to recognize that there are certain types of reactions happening here. In this case, zinc is going to form zinc 2 plus 2 electrons, because zinc is a more reactive metal than copper. On the copper side, copper 2 plus ions in solution gain 2 electrons to form copper. So in this case, we have reduction here, and we have oxidation over there. Now, what's important is that the zinc jumps into the solution and electrons are deposited onto the metal. That means that this electrode now becomes the source of electrons. And if it's a source of electrons, it is given the sign of negative. So it's connected to the negative terminal of the voltmeter. This is the positive terminal of the voltmeter. The electrons move in the external circuit from the negative towards the positive. This is the positive. And what we now need to recognize is that the name for this electrode here, where oxidation takes place, is called the anode. Please learn the definition that the anode is the place where oxidation takes place. And the way to learn it and remember it is just simply anox. Anode, oxidation. And over here, where we've got reduction, this is known as the cathode. And what do we look for? We look for a red reduction cat. And so it's very important that you are able to identify the anode and the cathode and recognize as well what connects these parts of the galvanic cell together, the two different half cells, is the salt bridge. Now, the salt bridge is filled with ions. It's a very soluble solution, something like potassium nitrate, and it completes the circuit. The positive ions in the salt bridge, those are known as cations. They move towards the cathode. So the positive ions, the potassium ions here, will move towards the cathode. The negative ions will move towards the anode. So NO3 minus, they will move towards the anode. And in this way, we make a connection. Positive ions moving one direction, the negative ions moving the other direction. There's a free flow of charge moving, and so it completes the internal circuit. But it also maintains electrical neutrality. What do I mean by that? Because we had more zinc ions being deposited into the solution, these negative ions neutralize that. Over here, copper ions are going to form copper metal, so the potassium ions replace the copper ions, and so overall, the two half cells remain neutral. Let's move on. And if we look at electrolysis in the electrolytic cell, we recognize here that these cells don't all look the same. But there's an important thing that's happening here. Chloride ions are losing electrons. So chloride ions are losing electrons to form chlorine gas, and we've got 2 electrons being lost. That is oxidation. And oxidation is taking place here. So this is the anode. Whereas over here we've got copper 2 plus 2 electrons to form copper metal. And what you'll recognize that is a reduction reaction. So that is the cathode. And recognize something in this reaction is that unlike the galvanic cell, this one is positive because it's the thing that is attracting the ions to the electrode, and this one is negative. So it's important to recognize that difference. Also recognize that galvanic electrolytic cells look different. You can get the ones for plating, but you can get, and they look quite different for the ones for electrolysis. But in exactly the same way, we're still saying that the anode is where oxidation takes place, and it's the positive cell. Whereas the spoon here is where reduction takes place, and it is the cathode. And I just wanted to show you that even for electrorefining, there's a solution with 2 electrodes, the same solution. The cathode is where you're going to get reduction, and the anode is where you're going to get oxidation. So nothing much has changed, even when you get to the chlor-alkali cell. Over here, one solution, even though there's a membrane cell between them, we still get the same sort of things happening. So be very clear about that. I want you to recognize that they all have electrolytes, and the galvanic cell, those can be molten or they can be in solution. There are 2 cells here. There are 2 half cells. And there's 1 cell usually here. Okay? If we go back to another comparison, they are usually different electrodes. They're different metals. These are usually either graphite or the same type of element. Although in electroplating we don't get that. So they do sometimes appear different. What I want you to recognize is very important, is in both cells we get oxidation at the anode and we get reduction at the cathode. Now, the last thing I wanted to show you is simply changes at the electrode. And the most important to recognize that, in fact, at the anode of a galvanic cell, we get a loss of mass. And at the cathode, we get a gain of mass. Now, in the same way, you'll see here, this one is the cathode and it's gaining mass as well. Now, that is for a metal that's being deposited. Guys, suggest that if you want to do these comparisons, it's a really good way to check your learning. So make sure that you analyze the difference between the electrolytic and the galvanic cell, and make sure that you can identify each case. Welcome back, everyone. Now that we've covered a summary of looking at redox reactions and comparing electrolytic and galvanic cells, let's go and have a look at some questions that we might want to apply our knowledge to as we go through this revision session. Now, if you look at this typical exam type of question, the first thing is that we're asked to look at the electrochemical cell. Now, you might think, oh, that's a strange term. We haven't often used that term. It's not identifying it, is it galvanic or is it electrolytic? But what we do recognize is that there's a voltmeter here, there's a salt bridge over here. We've got one half cell here, one half cell here. And I think you should be able to recognize, as we look at the diagram, certain information that they're probably going to ask some questions about a galvanic cell. Well, let's go and have a look at the questions. So the first question is, what type of cell is shown? Well, we've already said that this is a galvanic cell. Now, if I had to give you some further question and say, give me some reasons why it's a galvanic cell, what you'd recognize that in this cell, there's no battery. There's a voltmeter in the external circuit. So a galvanic cell is involved in transforming chemical potential energy into electrical potential energy. And because of that, we know it as a galvanic cell after Galvani, who discovered this cell and is the father of modern batteries. So we recognize as well that there's a salt bridge and that there are two cells. So it's definitely a galvanic cell. Next question. Write down the overall net reaction that takes place in the cell when it is working. So we need to be able to identify what's going on here. We've got a silver half cell and we've got a nickel half cell. Now, guys, I don't, at this stage, have much idea in terms of being able to guess which is the more reactive, which is the less reactive, which is the stronger reducing agent, which is the stronger oxidizing agent. To be able to get the values out and to get the proper reaction, I've got to go to the table of standard reduction potentials to compare these two half cells. Now remember, this table of standard reduction potentials was originally calculated because each of these half cells has been compared to the standard hydrogen potential cell, the standard hydrogen electrode. And based on that, we've been able to get quantitative readings of the differences. And that's what's found in our table. So my rule is that I look at the table of standard reduction potentials, and I'm going to start on the right-hand side. I'm going to look for my reducing agent. In other words, I'm going to look at the substance that is likely to be oxidized. In other words, if it's going to be oxidized, I'm looking for my anode. So all of those thinking steps is what leads me to look on the right-hand side here at the metal. And I'm running my finger down the right-hand side, and it can either be silver or nickel. And I haven't seen silver or nickel until I look over there. And that's where I see nickel goes to nickel 2 plus 2 electrons. And so there's no doubt in my mind that this is the reaction at the anode, because that's the oxidation reaction. However, let me go to the next part of the table, and I'm going to carry on going down to be able to see where I might find silver. And if I follow the rule down, I'll see, there's silver. Silver's not going to react. It's not a strong enough reducing agent. But the silver over here is a stronger oxidizing agent. So there's my oxidizing agent. And I recognize that's the reaction I'm going to need to write down. So to answer the question, I'm going to go back to the space that I've got, and I'm going to say, well, nickel went from the solid to nickel 2 plus 2 electrons. This is the oxidation half reaction. And immediately, I'm going to say, this is the anode. It's the source of electrons, and so I'm going to make that negative. Now, what about the other half reaction? Well, it's silver ions are going to gain an electron to form silver metal. I'm going to indicate that as reduction, because a gain of electrons is a reduction reaction. Remember, reduction takes place at the cathode. And so as I'm building up the answer to this question, I'm annotating on the diagram as well, because a later question might ask me to use that information. It's a very good exam tip to do, to add as much information on the question paper even if you don't write it all down on your answer sheet, but it helps your thinking. And so I'm definitely going to say this is the cathode. And it is positive, because the electrons are going to move from the anode towards the positive terminal. That's the movement of electrons. So in terms of my half reactions, I've not completed the question because it asked me for the net or overall cell reaction. So don't just write down the half reactions and identify them. You've done the hard work. It's important now to complete the job. So the first thing we need to recognize is we've got an imbalance. We've got 2 electrons that were given away and only 1 electron gained. To correct that imbalance, I'm going to multiply this whole reaction by 2. And now the electrons will cancel out, and I'm going to start writing down the net reaction. So I'm going to say nickel plus 2 Ag2 plus. Please write the ions in and recognize that this is an aqueous solution. That's a solid. It's the electrode. It forms nickel ions. And I'm going to put in the phase indicators here, plus 2 silver metal, which are solid. That's going to be deposited onto the electrode. And so there we have the net reaction. And we've been able to use that to identify what's the anode and the cathode as well. So let's go and have a look at the next question. It says here, which electrode, nickel or silver, must be connected to the negative terminal of the voltmeter? Now remember what we said. This is the anode, and it's giving away electrons. So this is the source of electrons. So this must be the negative. This is the positive. This is the positive terminal of the voltmeter. If we connected the voltmeter in the incorrect way, then the reading on the voltmeter would be in the opposite direction. So as long as we connect the negative to the negative and the positive to the positive, we will get a positive reading on the voltmeter. If we connect them incorrectly, it will give us a negative reading. So we want to make sure we connect the voltmeter properly. And so in this case, we have to connect the negative end of the voltmeter to the anode. So that's how we've done it. And so what we're going to say, the electrode must be the nickel electrode. So make sure the nickel electrode is connected to the negative end of the voltmeter, terminal of the voltmeter. Right, moving on. Write down the cell notation for the cell. Now, guys, this is not difficult. It's something that you've got to learn and make sure you stick to the rules. If they say under standard conditions, and they usually do, they want you to indicate the standard conditions as part of the answer. I'm going to put in both the phase indicators and the standard conditions into the answer so that we get it right. So we start with the anode, and we're starting with the electrode, which is nickel, and we're going to say that is a solid. Then we put a line to indicate there's a difference between the electrode and the other phase. And here we're going to say it's nickel 2+ solution, which is an aqueous solution. And because it's at standard conditions, we're going to say it's 1 mole per decimeter cubed. Now you can change the 1 mole per decimeter cubed to molar, that's fine. Double line to indicate the salt bridge. And then we're going to say we want some silver ions. And those silver ions are in aqueous solution, and they have a concentration of 1 molar. And then we get a silver electrode, which is a solid. And we must say at 298 Kelvin or 25 degrees Celsius. So the standard conditions of a galvanic cell are namely concentration of 1 molar per decimeter cubed at 25 degrees Celsius, and if it involves gases, and only if it involves gases, must the pressure of those gases be 1 atmosphere, 101.3 kilopascals. For this cell, we wouldn't need to say the gases for the standard conditions. Right, let's look at the last question for this section. What would you notice about the mass of the electrodes in the cell? Well, clearly, at the anode, we're going to find that the mass decreases. So there's going to be less nickel, but at the cathode, we're going to find there's going to be the mass increases. Because silver is being deposited onto that electrode. The silver cathode is going to get bigger and bigger, and the nickel anode is going to get smaller and smaller. Well, I hope you found those questions interesting, and I hope they've helped you revise some of the key points in answering questions about galvanic cells. What you'll notice is that they're quite predictable, and so it's worthwhile taking some time to learn how to answer these questions. Let's have a short break, and after that, we'll come and answer some more questions. Welcome back, everyone. Let's go and have a look at some more typical questions that we can get asked as part of the electrochemistry exam type questions. We might not cover everything, but we're going to try and cover as many interesting aspects of revising questions related to electrochemistry. So here we go. Consider the electrochemical cell below, and what you'll see is that we've got one cell. So there's the one container. We've got a concentrated solution of copper chloride in the solution. So we've also got a battery or a power source. So I'm sure that you'll be able to see from that that this is an electrolytic cell. It's unlike the galvanic cell. In other words, it's taking electrical energy and it's making and changing, producing chemical potential energy. So it's making a change in terms of chemical potential energy. It is not spontaneous, and it uses up energy to make this chemical potential energy in the form of a chemical reaction, where there's a change in the nature of the chemicals that we started with. So very important that you be able to identify these cells. Notice there's no salt bridge, there's one container, and there's a battery. There's no voltmeter in this scenario. Let's go to the next question, and you'll say, interesting, what type of power source is there? Is it an AC or a DC electrical power source that is used to drive this? Now let's think about that for a minute. If we had an AC power source, then that means that the sign of each of the electrodes would change continually. So at one moment this would be positive, and this would be negative, and a few seconds later this would be negative, and that would be positive. Well, that would be very confusing. And we know that it's the polarity of the electrodes that actually makes the reactions happen. If we kept on changing them, we would get different reactions happening at each of the electrodes all the time, and they would cancel each other out. So it can't be AC. This has to be DC. And so let's bear that in mind, that this is direct current. We're wanting a continual path of movement of charge in one direction. Now, I don't know if that's going to be the movement of positive charge or negative charge, but we want it in one direction, which is direct current. So the next question is a little bit more interesting, because it now tells us that this cell is used in the refining of copper. One of the electrodes consists of impure copper. When an electric current passes through the cell, the mass of electrode D increases. Is the electrode D the cathode or the anode? And we're asked to write down the relevant half reactions to support the answer. So there's a whole lot of information being given there, and we just need to recap it and make sure that we've recognized it and annotated it on the graph, on the diagram. It's always good to add information to the diagram. So the first thing I'm going to do is I'm going to take information from the question and recognize that there's an increase of mass at electrode P. So if there's an increase of mass at P, we also were told, there was one other thing. This is the refining of copper. One is impure copper and the other must be pure copper. So we've got two electrodes, one impure and one pure. We also recognize when we're refining copper, the pure copper is going to be where all the copper is going to be deposited. So I'm going to say P is pure copper. And that means that copper, 2+ ions here, are going to be changed into copper metal. That deposit is going to cause the increase in mass. And so if I had to write down the half reaction, we're going to say copper 2+ ions plus 2 electrons are going to form copper metal. Now, you could go and look that up on the standard reduction potentials, but it's not necessary. You know that you've got copper, pure copper, and you've got copper ions in solution. It can only be the reaction between copper and copper ions. So it's not difficult to see that this is the reaction. And if you look at it, it's a gain of electrons that is producing a deposit of copper. This is a reduction reaction. And reduction always takes place at the cathode, because we remember that we've got to look for the red cat. So, very interesting. For this answer then, we've got the relevant half reaction. We recognize that this is the cathode. So let's just put that in. So we've got it. And more important to recognize, this, because it's attracting the copper ions, must be negative. which means that terminal must be positive. Now, I don't know if they're going to ask questions about that, but I just like to add in the extra detail. If you're not sure why it's positive, let's just think that through, or why it's negative. Remember, for the ions to be attracted to the electrode, they've got to be attracted to the opposite charge than what they are. So the copper ions here are positive, and they're going to be attracted to the opposite, which is negative, to form this reaction where they're going to gain the electrons and they're going to form copper. Right. I think that was quite an interesting question, and I hope you've enjoyed looking at that. Remember, when we're dealing with these electrolytic cells, it's a separate question to the galvanic cells that you'll find in the final exam paper. But there are lots of different types of diagrams because there's not a standard diagram for electrolytic depending on how it's being used. We're not going to be able to cover all of them, but in this case we've done one of them, the electrorefining. So here's an interesting question about this impure copper. So remember, the impure copper was this side, and we're told that there are zinc impurities. So inside here, there's copper mixed with zinc. We know that there are copper ions in the solution, and we know that the copper is being deposited over there like that. We know this is negative, this is positive. Let's add on. So there's an initial reaction that's taking place. They tell us that the zinc impurities are going to form zinc ions. So zinc goes to zinc 2 plus 2 electrons. Now, how is that actually happening is just because zinc is a very reactive metal. If we look at the standard reduction potential table, we'll see that zinc is a stronger reducing agent than copper. Let's go and have a look at that, because that's exactly what they're asking in the next question. So if we run our finger down, remember, reducing agents on the right-hand side, we find that zinc is over here and copper is below it. Can't fit them all onto one table, but copper is down below it. So even naturally, we're going to find that zinc will form zinc 2 plus ions, and it will force the copper ions in the solution to gain electrons and to make copper go back. So the zinc ions in this solution are forced to become zinc 2 plus, and it's taking some of those and making the copper be deposited back onto Q as well. Even though when we connect these, the copper ions don't really want to be attracted there because that's positive. Copper's ions are going to be repelled. But the zinc is being oxidized there, maybe even before we turn on the cell. So now we're competing zinc ions to copper ions. We're going to say which of these are going to be attracted more to the negative terminal. Well, we've got to understand if they're going to undergo a gain of electrons, we've got to compare their oxidizing ability. So let's go back to the table, because that's exactly what they're asking. They say the relative strengths of the oxidizing ability, why zinc ions will not influence the copper deposit over here. So if we look at the table, you will see that zinc is very high up on the table. Look at the value, minus 0.76, whereas if you look at copper, it's one of the oxidizing agents. It is a reading of plus 0.34. So zinc is a much weaker oxidizing agent. Zinc, weaker oxidizing agent. In other words, you're going to need to give zinc a lot more energy to give up its status as a zinc ion in the solution. It doesn't like to become zinc metal. It's too reactive. So we would be able to say in the answer to this question that in fact what's happening is that we're seeing that copper is a stronger oxidizing agent, at least the copper ions are a stronger oxidizing agent, they will require less potential difference to be deposited on, and we can control the potential difference. Remember, this is a non-spontaneous reaction, and we'd be able to keep the potential difference low across the electrodes so that zinc isn't deposited. In that way, we ensure that there's a perfectly 100% deposit of pure copper on the electrode. So that's been quite interesting. Right, let's just wrap up the lesson by looking at a quick summary. Recognize that we've done much of this before. A galvanic cell, remember, it's taking chemical potential energy and converting it into electrical potential. Most important, oxidation is always at the anode, reduction always at the cathode. And remember that the salt bridge is the unique thing about the galvanic cell. It completes the internal circuit and allows a free flow of anions to the anode and cations to the cathode. Remember as well that for the galvanic cell, we can calculate the E naught of the cell, where we say E naught of the cathode minus E naught of the anode. And that will give you a positive value. It will always be positive because it is a spontaneous reaction. We're not adding any energy to it. So it's very important that when you do that reaction, you can calculate it and you can see how it works. If you go to the electrolytic cell, recognize that energy transfers from electrical energy into chemical potential energy, where the E naught of the cell is negative, it's non-spontaneous. We're needing to put energy in, whereas the oxidation reaction always takes place at the anode, even if it's electrolytic, and reduction always takes place at the cathode. So as we conclude now this whole summary on revising electrochemistry, I hope you've enjoyed it. Please study hard, and I wish you the best for your tests and exams. Bye for now.